Good morning, Joel and Luca. So we're now into our second week of looking at matrices, Unit 4 topic of matrices. Plan is to spend our lessons this week covering most of the rest of the content on the matrices course, well, all of it really, and then probably setting you an assignment to do, which we will review in the first lesson of next week. Then we're going to do Maclaurin's expansion as the other topic before half term. That's the plan. So anyway, this is a follow on from what we did last week on finding the inverse of a 3 by 3 matrix. And now we're going to use that to actually solve linear equations. So I'm going to recap with a 2 by 2 case, not just for the sake of recapping, but also to illustrate something to do with the different types of results that you get when you try and solve a simultaneous equation and how these show themselves in the matrix solutions that you get, if that makes any sense at all. So if I was trying to solve this using matrices, the first thing I'd do is I would rewrite that into some sort of matrix form by using the coefficients of the variables on the left-hand side as the matrix, multiplying that by the variables themselves and setting it equal to the result like that. Okay, so if you wanted to re-extract these original matrices, you would just realize that that times that plus that times that equals that, and that times that plus that times that equals that, and it works basically. So to solve this using matrices, what you do is you multiply each side by the inverse of this matrix. So what you're effectively doing is you're inserting the inverse of that matrix there, and you're inserting the same matrix, the inverse of that matrix there. And what will happen here is, because you're just timesing a matrix by its inverse, that will turn into the identity matrix and therefore effectively disappear. And you'll just have xy equals and then the answer. This is not new to you. We did this last year. So the question is, how do we find the inverse of this matrix? Well, it's very simple. If you've got a matrix A, B, C, D, then the inverse matrix is just the reciprocal of the determinant, which in this case would be 1 over AD minus BC, which we did last year as a determinant, and that would be multiplied by this matrix here, which would be DA on the leading diagonal, and then minus B minus C, like so. Interestingly, I don't know if I mentioned this the other day, this is exactly the same as when you find, oh crikey, what's Siri? Go away, Siri. Sorry about that. So this, what on earth was that? Oh, I'll just ignore it. So basically, this is done. This can be found in the same way as you do for 3 by 3 matrices. It's the reciprocal of the determinant times by the transpose of the matrix of cofactors. Oh, okay, so this is the matrix of cofactors transposed. The cofactor of A is D. The cofactor, so you cross out the row and the columns, it's D. The cofactor of B is minus C. The cofactor of C is minus B, and the cofactor of D is A. Anyway, it all works out, and that's the matrix. I'm blathering on a little bit now. So anyway, this will find the inverse of the 3, 2, 2 minus 1. This is from the notes. I'm just going to cheat and tell you that if you do that, the matrix you get, so the inverse matrix is actually, he says looking at it now, 1/7 of 5 minus 2 it's not, because I'm looking at the wrong example. Oh my gosh, what a mess. Right, bear with. I should do this correctly. What a nana I am. Here we go. it's minus 1/7 of minus 1, 3, minus 2, minus 2. Okay, it's just that applied to that. So anyway, if I now multiply each of these things in front by that matrix, the left-hand side will turn into xy, and the right-hand side will turn into minus 1/7 of minus 1, minus 2, minus 2, 3, multiplied by 5, 8. And if you work that out, it comes out to be 3 and minus 2. So x is equal to 3 and y is equal to minus 2. And we have what is called a unique solution. In other words, that is the only solution to that simultaneous equation at the start there. So why am I showing you all this? We did this last year because what's important for you to realise is that there are different things that can happen when you solve equations, systems of equations like that. And we're leading towards the point where you understand what happens in the 3×3 case. These are, of course, lines. But in the 3×3, not 3×3, in equations with 3 variables, they're not lines anymore. They're planes, as in infinitely sized sheets of paper in space. Okay, and when you're finding a solution to a set of planes, you're finding somewhere that lies on all 3 planes at the same time. A unique place where you're walking on all 3 planes at the same time. That's for later. For now, what we found is where we're walking on 2 lines at the same time. In other words, where the 2 lines cross. But that isn't guaranteed to happen. Okay, this is from example 2. And the second case is solving this equation. 4x minus 3y equals 2 and 8x minus 6y equals 4. Now when you go to try and solve this, you run into difficulties. If I turn it into the matrix form, 4 minus 3, 8 minus 6, x, y equals 2, 4. Then when you go to calculate the determinant, what happens is you get 1 over AD, which is minus 24, minus BC, so minus 24, 1 over. So when you go to calculate the determinant, you get that, which is equal to 0. Okay, and because it's equal to 0, you can't apply this because 1 over 0 isn't possible. So it all goes wrong. And the reason it's going wrong is because there is not a unique solution. There isn't one solution to this equation. In fact, there's an infinite number of solutions. And the reason that there's an infinite number of solutions is because these are effectively the same line. Okay, the 2 equations are basically the same thing. Therefore, any value of x and y that works in one equation is going to work in the other one as well. What we tend to do in this situation is we express our result by saying, well, let's suppose that x is a particular value, lambda. Then what could y be? Well, if we sub lambda into, say, the first equation and rearrange, I would see that lambda would be equal to, y, would be equal to, rearranging that, 2 minus 4 lambda over minus 3. Okay, something like that. So you can have any value of lambda you like, and that would lead to a solution. And all this is really is the equation of a straight line using a parameter, that straight line or that straight line there. So in this case, we say that the equations are consistent, but they do not have a unique solution. These are also said to be consistent. So these are also said to be consistent, but they don't have a so there's no unique solution. There's lots of solutions. Okay. So the third case is when there are no solutions at all. Okay, and this will happen when, so again, if we write the equation as a sort of matrix form thing like that, then again, when I go to do the determinant, so AD minus BC is going to be 6 minus 6, which is 0. So again, I get the same problem that the determinant is 0, therefore I can't use that matrix method of finding the solution. And the reason that I can't is because this time there are actually no solutions at all for this one here. This is the third case, and there are no solutions at all. And this has happened because these two lines are parallel to one another. In fact, if you try and solve this simultaneous equation, all that happens is you just get all the variables cancelling out with one another. So this is the third case, and in this case there are no solutions at all. There's not an infinite number of solutions, there are no solutions, and we say that the equations are inconsistent. You can't sub one into the other because it just disappears. So those are the three cases for the 2 by 2 situation. Now when we start to look at cases for the 3 by 3 situation, you will discover that there are in fact many more possibilities as to what can happen when you've got planes intersecting. But that's for next lesson, after we've done row echelon form, which is the other thing we've got to do next lesson. For today, I just want you to have a basic understanding of the idea of there being 3 cases for the 2 by 2 matrix: unique solution, no unique solution but an infinite number of solutions, and no solutions at all, inconsistent, and the reason that's happened is because the two lines are actually parallel to one another. So what about 3 by 3 then? Well, all we're doing today is just going through how to find the solutions to a 3 by 3. We're not going to worry about interpreting the situations when the determinant is 0, because for all the ones you're going to do on this, the determinants are not going to be 0 at the moment. So we put it into matrix form. Remember, these are actually planes. So we're looking to find out where the 3 planes intersect one another. So same again. Okay, and then you go and find the inverse of that matrix there. You apply it there and there. The left hand side becomes that. The right hand side becomes the inverse matrix, which he said, oh God, happens to be minus 1/28, minus 12, minus 10, 2, 2, 11, minus 5, 10, 13, minus 11, times by the 5, 3, 3, and all of that multiplied gives you solution 3 minus 1 minus 2. So I haven't gone through how to do that here because it's the same as last week. You find the matrix of cofactors of that, you find the transpose of that called the adjoint matrix, and you multiply it by the reciprocal of the determinant, which we also went through how to find last week. If you do all of that, you will find the solutions to that equation there. What I will do next lesson, rather exciting, is show you a completely different way of finding the solutions to that simultaneous equation using something called row echelon form. Okay, but that's for next time. For now, all I want you to do is to attempt the first exercise which I've attached to this video, to this lesson, and we'll pick the story then back up on Wednesday. Hope that was clear. It was a bit bumbly today. It's quite complicated and hard to explain over a video, but hopefully you get the idea. If not, just send me a message and I'll give you some help. Have fun!